Swayam Prabha. Digital India. Educated India.
So the last topic that we are going to take up in this course is detonations. We will spend some time talking about detonation waves. The structure of how we have proceeded is as follows. We went through the Rankine-Hugoniot relations at some stage, where we pointed out that the Rankine-Hugoniot, the Hugoniot curve breaks up into the upper branch and the lower branch, and the lower branch corresponds to the deflagration waves, and the upper branch corresponds to the detonation branch. And we then said we will now focus on deflagrations, right. Now the major problem that we had with the Rankine-Hugoniot relations was that we were assuming that there is a inherent flame speed associated with it, with which we could construct the Rayleigh line, because the Rayleigh line, the slope of the Rayleigh line is equal to minus m dot squared, where m dot is the mass flux of the flow that is passing through the wave, and that relates to the flame speed basically. Therefore by constructing a Rayleigh line, we presume that we know what is its slope, and that means we know what is the wave speed, but in reality that turned out to be the eigenvalue in the case of deflagrations, and we had to get into the structure of the deflagration wave in order to try to find out the flame speed there, and so a similar situation remains for detonations as well. So we will have to think about that at the moment. So but basically I wanted to the bottom line, I mean, or the commonality or the underlying thing about these things is we are primarily looking at premixed reactants, right. So that was the framework in which we did this. So from doing laminar deflagrations, which is essentially plain premix flames, we then moved on to diffusion flames and so on, not strictly in the framework of the Rankine-Hugoniot relations, but then we now going through all those things, we now come back to the detonation part of it, and then we ask the first question, what is the detonation wave speed, right. In doing this we recognize that we noticed at that time that in general even if you had what's called as strong detonations, they approach the Chapman-Jouguet detonation unless the system is overdriven, and weak detonations seldom occurred because it required highly reactive mixtures for the reactions to occur in such a high rates that you have the products that the reactions that are following the wave should happen at such high speed that when the wave propagates at supersonic speeds, you now have the products that are following at supersonic speeds as well, although not as fast as the waves themselves, the wave itself. So we were not necessarily concerned with weak detonations, and we noticed that strong detonations tend to become Chapman-Jouguet detonations. Therefore it makes sense for us to confine our attention to the wave speed of the Chapman-Jouguet detonation wave. So that's what we will do. Now in doing this, unlike in the case of deflagrations where we notice that the wave speed is actually an eigenvalue of a eigenvalue problem looking at the structure of the wave, where we have to do the mass and energy balances across the or through the wave rather, here we notice that the deflagration wave, sorry, the detonation wave is traveling at supersonic speeds, so it quite doesn't really know what's ahead of it. The information doesn't propagate upstream. Therefore it should be possible for us to actually try to get the wave speed without having to get into the structure. So in the case of deflagrations, we had this heat conduction that was happening upstream from the reaction zone that was heating up the reactants, whereas in the case of detonation wave, the detonation wave keeps going and it does not really know what is ahead. Therefore we can't really hope to actually look at the structure in order to resolve the wave speed. So there must be a trick that is involved somewhere here, and I will highlight this trick as we go along, but we will pretend that for the moment that we do not have to necessarily go through the structure. We will just keep going, looking at the kind of Rankine analysis similar to Rankine-Hugoniot analysis, and then see where we can try to exploit the nature of detonation to look for the wave speed. So for the Chapman-Jouguet wave, or particularly Chapman-Jouguet detonation, in this context, the product speed is basically the speed of sound. So unlike, for example, in a normal shock where the downstream velocity is always subsonic, when the upstream velocity is supersonic, in the case of a Chapman-Jouguet wave, the downstream velocity is always sonic, locally at the speed of sound. So the speed of sound behind the detonation wave is, we use the same notation as what we had before, A infinity equals square root partial derivative of pressure, the downstream pressure with respect to the downstream density at constant entropy, constant downstream entropy. Now here U infinity equals A infinity at the upper Cj point, in the Hugoniot curve. So we have m dot equals rho naught u naught equals rho infinity u infinity, which is now equal to rho infinity A infinity. So from here u naught is equal to 1 over rho naught rho infinity A infinity. Now A infinity is equals square root of gamma infinity R infinity T infinity. So u naught equal to rho infinity over rho naught square root of gamma infinity R infinity T infinity, right. So let us call this relationship number 1. So here what the problem is, u naught is actually what we are looking for. This is very similar to what we did for the deflagrations, okay. That is related to rho naught, also very similar to deflagrations, because there also we were actually trying to look for a relationship for m dot versus the rest, and m dot is rho naught u naught. But here what we now find, see this is the problem, what we find is the wave speed, which is essentially in a flame fixed coordinate system or a wave fixed coordinate system, it is essentially u naught, depends on the downstream quantities, right, rho infinity, gamma infinity, R infinity and T infinity, and that is the problem. So we now have to try to find out if we can evaluate those quantities, right. So note that the wave speed, which is essentially u naught, depends on the burn gas properties. As a matter of fact, we also know that, for example, in the lower Cj point as well, u infinity is equal to A infinity, right, and m dot being equal to rho naught u naught equal to rho infinity u infinity is valid regardless of where we are on the Hugoniot curve, right. So if you now plug in u infinity equal to A infinity, that's valid for both upper Cj and lower Cj points. So strictly speaking, this could be a Cj detonation wave or a Cj deflagration wave at this moment, right. So we haven't quite, strictly speaking, exploited the fact that we are particularly interested in a detonation wave at this stage. So keep that in mind and look for where we are doing this. So what we want to now try to do is to explore or chase the evaluation of the burn gas properties. So let's try to do that. One itself implies that rho naught squared u naught squared equals m dot squared equals gamma infinity p infinity rho infinity. You can actually get this quite easily. Now in the Rayleigh line, we have p infinity minus p naught divided by 1 over rho infinity minus 1 over rho naught equals minus m dot squared. And then we plug this in here, right. So from this we can get 1 over rho naught minus 1 over rho infinity. We swap this so that we can get rid of the negative sign in the m dot squared. So that would be p infinity minus p naught divided by gamma infinity p infinity rho infinity. That's coming from here, right. Now let's call this 2, and this would be pretty interesting and important at some stage in the future. From now on, what we are going to do something that could be a little bit boring, all right, but we will come back to this and say, well, we can forget about everything that I said, which is kind of complicated and boring, but we can just go back and look at this and then see if we can exploit something here. So let me just go through whatever needs to be gone through, and then we will come back to this. So here what we want to do is multiply above by p naught plus p infinity. So we have p naught plus p infinity times 1 over rho naught minus 1 over rho infinity equals, we now get p infinity squared minus p naught squared divided by gamma infinity p infinity rho infinity. So why did we do this? This is where we are now going to make the point that we are looking at a detonation wave. We have already made the point that we are looking at a Chapman-Jouguet wave, right, and we pretended to be doing detonation, but not quite yet until now, right. So what we want to do is to notice that across a detonation wave the pressure increases manifold, right, so many times, and therefore p infinity is larger than p naught, quite larger than p naught actually, right. Now what we don't want to do at this stage, at this step, is to say that p infinity is much larger than p naught. So I used the words carefully there. I said quite larger than, not really much larger than. So if you now say quite larger than, right, then we can then easily say that p infinity squared is much larger than p naught, okay, p naught squared. So what we are going to right now do is to say, suppose p infinity squared is much larger than p naught squared. This is much less of an approximation when compared to directly supposing that P infinity itself is much larger than P naught. Okay, so this is all right. This is okay. But what we are going to do, what we will find is this is not going to really help us directly. It's going to lead us to go into some circles, and then we will come up with an iterative scheme of solving this, right? So that's the boring part that I was just talking about, and then we go through all that, and then I'm going to come back and say, wait, for an engineering purpose, can I relax and say I don't want to actually multiply by P naught plus P infinity here and then get this P naught squared to be considered to be much larger than P naught squared. Directly in 2, can I say if P naught is P infinity itself is much greater than P naught, okay, instead of looking at the squares. I'll do that quite some time later, okay, but this is the point where we are beginning to talk about detonations. That's essentially the idea, and this allows us to get around the structure of the wave, okay. By recognizing this, we don't have to bother about getting the structure of the wave, unlike we did in the deflagration, but there the physics demanded it, okay. So the upstream conduction demands that we consider the structure of the wave. Here we didn't have to do that. Instead we actually short circuited by going through this approximation. So now let us suppose we will now continue to assume that P infinity squared is much greater than P naught squared, and that's going to imply that P naught divided by rho naught minus P naught divided by rho infinity plus P infinity divided by rho naught minus P infinity divided by rho infinity, that's opening up these parentheses here, that's equal to P infinity divided by gamma infinity rho infinity. That means we have got rid of the P naught squared, so we remain with P infinity squared. One of the P infinities there gets cancelled with the one at the bottom, so you get only this at the right hand side, and so you use the equation of state. R naught T naught minus rho naught divided by rho infinity R naught T naught plus rho infinity by rho naught R infinity T infinity minus R infinity T infinity. That means wherever we have a P infinity by rho infinity, we use an R infinity T infinity. P naught rho naught, P naught over rho naught, we use R naught T naught. But when you have this mixed kind of quotients, we now take the ratios of densities and then use the equation of state wherever applicable, and that's going to mean that on the right hand side we also write R infinity T infinity divided by gamma infinity. So multiply, this is the kind of boring part I was talking about, so it's basically some algebra that we go through. Rho naught divided by R infinity T infinity, and that's going to get you a quadratic. You might recall doing something like this with the Hugoniot curve and the Rankine and the Rayleigh line put together earlier on to get the upstream Mach numbers, but here our goal is slightly different. So we get rho infinity over rho naught the whole squared minus 1 over gamma infinity plus 1 minus R naught T naught divided by R infinity T infinity times rho infinity over rho naught minus R naught T naught divided by R infinity T infinity equal to 0. Let's call this 3. Now this is a quadratic in rho infinity over rho naught, right. Now but you see what are the coefficients? The coefficients involves gamma infinity, R naught, R T naught, R infinity, T infinity, right. So those are the coefficients there. So solving this will give rho infinity over rho naught in terms of gamma infinity r naught T naught r infinity T infinity, right. So of course we are still chasing, that means we wanted to go back here and then say can I get rho infinity? Well, you can, but it's going to be in terms of gamma infinity r infinity T infinity. We need to know those things as well, right. So that's okay. So we are not introducing anything new, we are trying to count only the old things, so that's all right. So we can easily now also use P infinity is related to rho infinity by rho naught and T infinity by essentially the ratio of equations of state at the product and reactant conditions. So that is P infinity equal to rho naught divided by rho infinity r naught T naught divided by r infinity T infinity times P naught. So let's call this 4. The reason why we number these equations is we will now go through an iterative procedure, iterative solution procedure. The first thing we do is assume a P infinity. We don't know what P infinity is, but let's assume it. And did I make a mistake? Right. P equals rho RT, so we need to have P infinity equals is that right? I want to make sure I don't make that mistake, but I did. So assume T infinity 3. Now next thing we do is calculate the equilibrium composition. Yi infinity based on P infinity and T infinity. That is assumed, that is once you get to step 3 you have a P infinity and T infinity to work with which you now use the equilibrium composition there. And then so once you do this you now use the energy balance and to check whether this is going to resolve things. So check for E infinity from the Hugoniot relation. In fact we had the mass balance here and the Rayleigh line is a combination of statements of mass conservation and momentum conservation. That is what we have been working with. We have never used energy conservation yet, so we will try to use that as a check, right. So we will try to use the Hugoniot relation. We had H infinity minus H naught equals 1/2 1 over rho infinity plus 1 over rho naught times P infinity minus P naught, and which means the sensible enthalpy part of it, Hs infinity minus Hs naught. So what we do is we now split this in the sensible enthalpy and heat of formation. So the differences in the heats of formation of the products and reactants altogether is the heat release, right. So that is Q, so that would be Q plus 1/2 1 over rho infinity plus 1 over rho naught times P infinity minus P naught. Here then we want to use the internal energy, that is but Hs, the sensible enthalpy, is equal to internal energy plus P over rho. Therefore Hs infinity minus Hs naught equal to E infinity minus E naught plus P infinity over rho infinity minus P naught over rho naught. Okay, let's now substitute this up there. Substitute this in the Hugoniot. Then we get E infinity minus E naught equal to 1/2 1 over rho infinity plus 1 over rho naught times P infinity minus P naught minus P infinity divided by rho infinity plus P naught divided by rho naught plus Q. So simplify this, you have some opportunity to cancel things, therefore we get E infinity minus E naught equals Q plus 1/2 P infinity plus P naught times 1 over rho naught minus 1 over rho infinity. So here we can now go back and use this relationship number 2, and what do you get? You get a P infinity plus P naught over here, that is what we tried to multiply. But then if you now use 1 over rho infinity rho naught minus 1 over rho infinity as this, you naturally get a product of P infinity plus P naught times P infinity minus P naught, which will lead to P infinity squared minus P naught squared, right. So using 2, E infinity minus E naught equals 1/2 P infinity squared minus P naught squared divided by gamma infinity P infinity rho infinity plus Q. Here again you now try to approximate, saying P infinity squared is much greater than P naught squared, and therefore that is going to lead us to a E infinity minus E naught that is equal to 1/2 P infinity divided by gamma infinity rho infinity plus Q, and P infinity over rho infinity is R infinity T infinity, therefore this is R infinity T infinity divided by 2 gamma infinity plus Q, which is E infinity equals E naught plus R infinity T infinity divided by gamma infinity plus Q. So if you call this 5, then we have assumed a T infinity So the equilibrium composition is also now going to give you a gamma infinity and R infinity, right. So now you have, for the assumed value of P infinity and T infinity, you get gamma infinity and R infinity, with which you can check, right. So check if the above equation is satisfied, right. So once you know that this is satisfied, you're okay with the choice of T infinity that you made in step 2, alright. Of course you still have the outer loop of having assumed a P infinity. So once you do this, solve for, so this is step 3 that we have just finished. Step 4 would be solve for rho infinity over rho naught using the quadratic equation, that's number 3, right. And step 5 would be find P infinity from 4, that's here, right. Then 6, check if this is the same as assumed, right. So whenever we say check, we would like to think about two things. One, it's always within a certain tolerance, okay. So you're not going to exactly match, maybe you can match with to the first decimal place, second decimal place, third decimal place, or as a percentage, whatever it is. You want to hold to a tolerance, and if it is satisfied then you proceed. If not, then you have to repeat the inner loop, right. So in this case, for example, you now assume T infinity and then you go through this check, and if you are satisfied within the tolerance you proceed. If you are not satisfied within the tolerance, right, then you assume a different T infinity in step 2, go through the check for the assumed P infinity, and then once you have converged on a T infinity, then you proceed to step 4, step 5, and then check. So in check, of course it's within a tolerance, and within the tolerance if you have not satisfied, then you have to go back and change your P infinity, go through the whole thing again, right. So you do this. Of course it's a bit of a tedious process. So once you do this, so finally step 7 would be, once P infinity, rho infinity, T infinity and R infinity are finalized, use 1 to find U naught. That's almost like the post processing, right. Now of course we find that there's kind of like a loop within a loop, and it's going to take a while for you to converge. So instead of going through this, the next best thing that you can do, as I pointed out earlier, is don't push yourself to assume P infinity squared is much greater than P naught squared. Directly say, can I adopt P infinity itself as much greater than P naught, right. So a good approximation is to directly use P infinity itself as much greater than P naught in 2, right. That's what I said we will go back to. So that implies 1 over rho naught minus 1 over rho infinity equal to, we earlier had P infinity squared minus P naught squared divided by gamma P infinity rho infinity. We threw away P naught squared in preference to P infinity squared, cancelled one of those P infinities at the top with one at the bottom and so on. But now we have a P infinity minus P naught divided by gamma P infinity rho infinity P naught is thrown away in comparison with P infinity. The P infinity directly gets cancelled with the one at the bottom, so you're left with only 1 over gamma infinity rho infinity, right? So this means that rho infinity over rho naught is simply equal to gamma infinity plus 1 divided by gamma infinity. Hs infinity minus Hs naught equal to q plus 1/2 P infinity minus P naught times 1 over rho naught plus 1 over rho infinity. In fact, we've just written it here, still around. So here what we want to do is this is something that we did during the Rankine-Hugoniot days, that is, we want to write this as gamma infinity over gamma infinity minus 1 P infinity over rho infinity minus gamma naught divided by gamma naught minus 1 P naught over rho naught. The way we get this is we now say Hs infinity is Cp infinity T infinity. Cp infinity is gamma infinity or infinity divided by gamma infinity minus 1, and then you had a T infinity or infinity. T infinity is P infinity divided by rho infinity. Similarly for the not conditions. So if you now do this, and then the next step you do is you notice that you're not going to have a big difference in gamma infinity and gamma naught between the two, okay. To think about this, gamma is basically ratio of specific heats. Ratio of specific heats depends on whether the gases are monatomic or diatomic or polyatomic, whether it's linear polyatomic or non-linear polyatomic, and so on. Now if it's monatomic, you're going to have something like so if it's diatomic, you're going to have something like 1.4. If it's monatomic, it's going to be like 1.6, 67, and so on. And if it is polyatomic, you may have something less than 1.4, right, 1.3. So all these things are around of the order of 1. If you now think about orders of magnitude, it's all of the order of 1. And mostly for mixtures of gases in both cases, it's going to be in general a polyatomic system, and so we expect that we don't even have this variation, right. So we don't expect a big difference between gamma infinity divided by gamma infinity minus 1 and gamma naught divided by gamma naught minus 1. So for an order of magnitude point of view, we notice that just like how we now threw away P naught itself as opposed to P infinity, right, we now say let's get rid of this entire term. Alright, so if you now do, and similarly we can do it here as well in preference to P infinity. So wherever we find P infinity minus P naught kind of thing, you now get rid of this. So with this we now say gamma infinity divided by gamma infinity minus 1 times P infinity minus 1/2 P infinity times rho infinity divided by rho naught plus 1 equals rho infinity q. Some more simplification, well, basically you can pull out P infinity, alright, and then plug your rho infinity over rho naught as gamma infinity plus 1 divided by gamma infinity here, and pull this P infinity out. You had something in terms of gamma infinity here. This is also going to be in terms of gamma infinity. So you'll now have one big function that's gamma infinity, that's in terms of gamma infinity. So quickly going through that, divided by gamma infinity minus 1 minus half gamma infinity plus 1 divided by gamma infinity plus 1 equal to rho infinity q, and then you put things together. So we get P infinity times gamma infinity plus 1 divided by 2 gamma infinity times gamma infinity minus 1 equals rho infinity q. But then keep in mind that this itself after the simplification still has remnants of rho infinity over rho naught, right. So, and this rho infinity then gets cancelled with that, right. So then you get P infinity equal to 2q rho naught times gamma infinity minus 1. Now if you did not make a big fuss about having to find gamma infinity, of course you can assume equilibrium, find the composition and so on, but the idea was you don't go through all that, right. That means you now say let's not worry about the variation of gamma between reactants and products, you assume some gamma that's common and known, then you directly get a value for P infinity just knowing the heat release and the density of the reactants, right. The interesting thing here is Q is like joules per kg and rho naught is kilograms per meter cube. So rho naught Q is like joules per meter cubed. So this is basically something like a volumetric heat release of the reactants, right. That means the denser the reactants, greater the pressure, alright. That means denser the reactants, it compacts more heat within it, okay, per unit volume, and that means greater the downstream pressure. In fact we have been exploiting the notion that the pressure itself is much greater than the initial pressure, and that's really the hallmark of detonation waves. So what's actually great about detonation waves is not as much about the kilometers per second kind of velocities, but what is utilized in a detonation wave in terms of applications is the pressure. So you have this huge pressure build up behind the wave, and as the wave propagates it now has a rarefaction that follows it, which sucks everything in and then destroys the materials that it passes through, or the matter that it passes through. So here what we are basically seeing is we are actually talking about gases all over, but if you now think about reactants that were actually in solid form and correspondingly you gave rise to some heat, okay, because of the gas evaporating and then reacting, the solid evaporating and giving rise to the detonation wave in the gas phase, alright, then the volumetric heat of the reactants is a lot higher, and therefore solid detonation reactants give rise to a much higher increase in pressures, right. So you get this physically meaningful relationship from making this approximation here and proceeding instead of getting stuck in this iterative loop. So finally, so now we want to go back to 1 and say U naught is equal to 1 over rho naught square root of gamma infinity P infinity rho infinity. That can be written as 1 over rho naught square root of gamma infinity P infinity rho infinity over rho naught times rho naught, and therefore we can write this as still we got the rho naught there, and so we can write this as square root of gamma infinity P infinity divided by rho naught times gamma infinity plus 1 divided by gamma infinity. Cancel the gamma infinity, equal to gamma infinity plus 1, and so the gamma infinity gets cancelled, and P infinity divided by rho naught is 2q times gamma infinity minus 1, that's equal to square root of 2 gamma infinity squared minus 1 times q. So what we can see is, note that P infinity goes as Q, but U naught goes as square root of Q. So you don't quite get the same effect out of the heat release. And let's just push this a little bit more, and we are pretty much there to see the result here. So since P infinity equals 2Q rho naught times gamma infinity minus 1, P infinity divided by rho infinity is equal to 2Q rho naught divided by rho infinity times gamma infinity minus 1. Then whenever you see a rho infinity over rho naught, plug in a rho infinity gamma infinity plus 1 divided by gamma infinity. So you say 2Q times gamma infinity minus 1 divided by gamma infinity plus 1, and that gives you Q equal to, so P infinity over rho infinity to start with is, put it this way, this is nothing but R infinity T infinity, which is RU T infinity divided by W infinity, right. So from here we can get Q, trying to put these two together, right. Q is RU T infinity divided by W infinity times 1/2 gamma infinity plus 1 divided by gamma infinity times gamma infinity minus 1. So from here what we can see is Q goes as T infinity divided by W infinity, and then putting these two together, right, we have U naught essentially goes as T infinity divided by W infinity to the half, right. Now for those of us who are familiar with rocket propulsion, we get a very similar result for the exit velocity of the rocket from a gas dynamic nozzle undergoing supplied by combustion gases at a temperature T infinity and molecular weight of gases being W infinity, right. And this is what translates to something called a specific impulse. Now if you have a detonation engine, pulse detonation engine, the detonation wave keeps on propagating out and at this speed, and what we find is that the speed of the wave is also directly proportional to T infinity divided by W infinity to the power, the same dependence. So effectively a pulse detonation rocket engine is not going to have a specific impulse that is way too different from a ordinary chemical rocket. So there is no way of beating around nature in this case, right. So we are pretty much going to get the same result as we can see from this.